So I promised to show Leray-Hopf theorem, and here we are. So the theorem is you have L3 and locally H1 solutions of the backward, so Navier-Stokes in backward self-similar variables. And we would like to say that in fact these don't exist. Okay, so I'll go now straight to the point. Okay, so we make a proof, and I'll assume something. So maybe, okay, philosophically, solution of this equation are expected to be smooth, because because now if we look in terms of critical spaces, something like H1 for the stationary problem is okay. L infinity in H1 for L infinity time H1 space is a subcritical space for Navier-Stokes. So for this kind of solutions, we expect smoothness. Fine. Smoothness gives us something more, which is that these solutions decay. So I'll assume in this proof, and this comes from the regularity theorem, but I don't want to enter this. So assume that U and P are smooth, and that U and P together, possibly with their derivatives, decay. In particular, I want this decay U of xi is controlled by C divided by xi to the, so each derivative gains one level of decay, and there is a basic 3 plus. And then assume that the pressure is bounded by C to the 2 plus K. We don't need much, we will need probably one derivative. But this is true, so the constant depends on K, and it's true for every K. So this is literally true, follows from the regularity theory. I don't do it now, simply. Okay. What is instead that we want to do? Okay. We stare at our equation, and we see that now there is a part coming from the self-similar variables. So these two terms coming from the self-similar variables are not there in Navier-Stokes. This one is the nonlinearity of Navier-Stokes. This one is the Laplacian. In the two terms that appeared through the self-similar variables, there is one which looks like a transport term. So it's kind of natural to introduce U tilde to be the guy advecting the rest. So xi over 2 plus U. So U plus xi over 2. OK. So let's rewrite the full equation of this quantity. Maybe I do it in color on the equation. OK. Laplacian of U tilde is equal to Laplacian of U. So this first term is easily rewritten. Then, so this one we said is now U tilde that wants to advect U. But now I want to take out U of the equation, so let's write U in terms of U tilde. U is U tilde minus xi over 2. So this becomes this minus U tilde dot grad xi over 2. OK. U tilde dot grad xi over 2, though, is, so this gradient of xi is the identity. This is 1/2. So here we have 1/2. This is, let me rewrite like this. This is minus 1/2 U tilde. U tilde, yes, this is minus 1/2 U tilde. But we have a U over 2 in the equation here. So let's write this as minus 1/2 U minus xi over 2. I go back to U just because this and this then cancel out, no? And then the xi over 2 becomes xi over 4. Xi over 4. Yes. And xi over 4 is a nice term because it's a gradient of something. It's the gradient of modulus of xi squared over 8. Okay? So a gradient is something that we can put back in the pressure. So let's do it. We define now the pressure, P tilde, to be the old pressure. And now I will never make the sign correct. But let's try xi over a squared over 8. I'm not sure if I wrote this. Okay. Okay, it should be. So if I introduce these two objects and I look back at my equation, now what I've written here is Laplacian of u tilde plus the nonlinear term, and then plus the gradient of a pressure equal to 0. So, sorry? Minus Laplacian, thanks. And this is stationary. I mean, looks like stationary Navier-Stokes, but it's not really because when I do this, when I introduce this u tilde, I change the divergence. The divergence of u tilde now it's not 0 as in stationary Navier-Stokes, it's 3/2. Okay. And now here comes the magic, or the computation that is surprisingly true. We introduce a quantity which, one can motivate it, but I'll do the computation directly because otherwise it gets too messy. Okay, this is a quantity, it's not surprising. And the surprising, and then you add the pressure to it, okay? This quantity, okay, so this is a new definition, and I can write it back, I lost it, in terms of the u and p. This is 1/2 modulus of u of xi squared. Then I have the plus xi over 2, so I have a term which is xi scalar product with u over xi. And then I have a plus modulus of xi over 2 squared, which cancels the one inside this pressure. So then I have plus p of xi. Okay, so I wrote it back in terms of the original u and p, because later we will use it. And the reason why we consider this, sorry?
There's a 1/2 xi u xi.
There is a?
1/2.
No, because it's the double product, no?
Yeah, but it's xi over 2.
Yes, but I do the double product, I do 2 times this times this. There is a 1/2, thanks. Good point. So, okay. Okay. Now, the important property of this, thanks. This is important because otherwise nothing will close up, is that now I want to look at an operator of this applied to this, which is this one. I want to apply this operator to pi. And I guess the way originally it was found, if I can imagine, was, if you want to find it without knowing this quantity, you compute this operator applied to u squared, which is a computation you are led to do by many means. And then you realize that if you add the pressure, it closes up. Okay. And what I claim is that this object has a sign. So now I compute, I will say that this is positive. No, it's and it's wrong. Of course, I put a minus. So I'll prove it's negative. And this operator, so this is Laplacian, this is as a maximum principle. I mean, if you sit at a maximum, then the operator, and the operator has a sign, so and if you are a super solution of this, then your maximum is on the boundary. This will be the second step I will do. But first, let me try to give a sign to this thing. OK. I have to apply minus Laplacian. Minus Laplacian of something squared is over 2, is minus Laplacian u tilde minus du tilde squared. OK, and then I have to subtract the Laplacian of p tilde. And then I have to do plus u tilde dot grad. And I have the two terms. Let me write them, u tilde over 2 plus p tilde. This is the quantity that I need to compute. And here, on this term, minus Laplacian, I use the equation, which tells me minus Laplacian is minus this other stuff. So this is minus u tilde dot grad u tilde. Minus gradient of p tilde, u tilde. OK? And I start realizing a cancellation that I like a lot between this term and what appears here. So let me maybe I'll write it all, because otherwise I mess it up. So here I want to write Laplacian of p tilde. And then there is u tilde squared over 2 plus u tilde dot grad p tilde. OK? So this term disappears with this one. And now,
there's minus modulus of du squared.
Thanks. OK? So now, OK, the first term and this one, u tilde, this one is the same as this one, right? So I'm left with minus du tilde squared and the Laplacian of the pressure, of the new pressure. What is the Laplacian of the new pressure? Well, there are several ways to find it, but so either I go back and I recall that the Laplacian of the pressure has an expression, blah, 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 or I go to this formula and I remember what is the way to find the Laplacian of a pressure. It's to take the divergence of this equation. So Laplacian of p tilde solves minus, OK, the divergence here, the Laplacian of 3/2 is 0. So I have only the divergence of this term, u tilde grad u tilde. And this I rewrite in coordinates. So this is minus di u tilde j dj u tilde I. OK. And here, what do I observe? When di falls here, I get minus di u tilde j dj u tilde I. When the di falls here, OK, now di u tilde is not 0, it's 3/2. But since I'm taking a further dj, vanishes. So formally, the pressure solves the same equation. I mean, the pressure tilde solves the same as the old. Okay. So I use it here. So here I have minus the Laplacian of the pressure. I get that this is di u tilde j, dj u tilde I, but this is exactly a quantity the way I assign. Okay. Now, so step 2, okay, this equation has a maximum principle. Which means that if you want to consider the maximum of pi, let's say over R3, well, this will be the limit. Let's sit on a finite domain. This will be the limit of the maximum of pi onto a ball BR. Sorry, limit over R going to infinity. But now the equation has a maximum principle. So this maximum is reached on the boundary of max over the boundary of BR of pi. But that's where the information coming from the regularity, so the decay of U enters into the game. U and P decay at infinity, so this the maximum over the boundary of a ball goes to 0. It's like 1 over R to a power. So, so overall, pi is negative. Okay. So it's a new signed function that we build around something of Navier-Stokes. Now we know we can kill a lot of things with it. Okay, the way to, so when you get here, you know you have a lot of information. The way to finish, to me, is still non-trivial. And, okay, so pi is negative, so this one is the one I know. Pi is negative, so it's, it has an integral, and possibly minus to infinity, and the integral must be negative. Okay. Then by monotone convergence, this integral I can, so now I want to compute the quantity in 2 different ways and get that U has to be 0 from it. Okay. This is the limit of the integral of pi against a function, okay, that I will call phi of epsilon xi, where phi is a C infinity. So this is phi. C infinity compactly supported radial. It will be important to take it radial in xi. And so phi of epsilon xi for epsilon small will be something like this, no? So it approximates 1, okay? And now I compute this quantity. So now I remember pi as 3 terms. So this is the limit of the integral of, okay, the integral of u squared. Now here you see that there is something. So the integral of u squared, so u squared over 2. So this one is clearly goes to the integral of u squared over 2. And it's a positive quantity. And then there are the other 2 contributions. Xi over 2 u of xi times this phi of epsilon xi. And this seems here, but it's not in reality. So this integral is 0. And the reason is that xi over 2 phi is the gradient of a new function, no? These 2 when you have a radial function times psi, this is the gradient of something, let's say. And gradients are orthogonal in L2 to divergence free. So this term, so this integral, so this is 0. And the third term is pressure. Multiplied by this. And so the question is if the negativity of the pressure can compensate for the positivity of this term. Otherwise, we have a contradiction. I mean, we find that U is 0. And the lemma says, no, it's not strong enough. But this is the lemma I find still mysterious. Because, I mean, it says that this limit is not that one, but it's that one up to a constant. Which. So the lemma that we will need is the following, that if you have a solution of Laplacian P equal, and here you can have a term of the form Dij Fij, with these Fij are simply L1 intersected L2 functions, then the limit epsilon to 0 of the integral of P phi of epsilon is minus 1/3 the integral over R3 of the sum of Fij. So over I and j. Okay? And okay, from this lemma with the Fij equal, so applied with Fij equal Uj, okay, we find that, okay, we find what? We find that this limit, okay, no, here, sorry, I'm wrong. Here it's not Fij, it's Fii, sorry. Sum of I from 1 to 3. So when I apply this, I get the modulus of U squared here. So I get that this quantity converges to U squared over 3. Yes, with a minus. But now this concludes the proof because we have a U squared over 2 minus U squared over 3. This is U squared over 6, but it has to be less or equal than 0. Okay, so we are left to prove this lemma. Okay. Fourier, yes.
Please. U is there is the additional term psi over 2 dot gradient of U has no contribution when you take the divergence of. No, sorry. When you apply the lemma, so I think you're implicitly saying that minus Laplacian of P should be Dij
UIUJ. This is the original pressure for the.
But the original pressure means the pressure in self-similar variable, right? That is the extra term.
Yes, in self-similar variables, the pressure solves.
So the divergence of this term has 0 contribution?
It must, yes.
Derivative in time.
Sorry?
Because its derivative in time has 0 contribution. When we write the Laplacian of the pressure equals divergence of U cross U, it's because we did the dt of divergence of U is 0. So it's that.
Okay, yes, this is a reason. Or if you want, the pressure before going to self-similar variable solved that. And when you write the equation for the pressure in self-similar variables, you find exactly this. I mean, that the pressure solves this with UIUJ. So proof of the lemma, Fourier. So the integral of p phi of epsilon dot, new Fourier transform gives the integral. Okay. And then I have the Fourier transform of phi. So I'm using Plancherel. Then I have the Fourier transform of P. But I use the equation. The Fourier transform of P is xi I xi j divided modulus of xi squared. And there is a minus. And then I have the Fourier transform of Fij. Okay. Perhaps I have a complex conjugate somewhere. Okay. And now, okay, what is the Fourier transform of this? This is the Fourier transform of phi evaluated at dot over epsilon with a 1 over epsilon cube outside. And now, how do I conclude? Okay, now I do a change of variable in order to have back here. So the 1 over epsilon cube goes away with the change of variable. So I'm left with xi I xi j modulus of xi squared Fij hat evaluated at epsilon psi. And then I have phi hat of psi. And now how is this one? Okay, when I let epsilon to 0, this one converges, so the Fourier transform is continuous, so I evaluate in 0. So I'm left with f hat ij at 0. And then I have the integral of xi I xi j over modulus of xi squared. Phi hat of xi. Phi was a radial function. And so when I integrate, for I different than j, I'm integrating something which integrates 0. And when I is equal to j, here I have the modulus of xi squared cancels. I have the integral of phi hat by Fourier inversion formula. I find back the value of phi, which was 1 at 0. Okay. So 0 if I different from j. And now, where did I miss the factor 3 in all this story? Do you see a factor 3? This now seems to me f hat ij, so fi hat I high at 0, phi at 0. I'm sorry, the factor 3. Correct. This is like psi 1 squared over xi squared. This is not 1, it's not as it simplifies, it's 1/3 because the integral, if I sum the 3 variables, thanks. Okay. Are there questions? Yes.
In the highest dimension, like if a fixed dimension D,
Huh.
in principle, someone believes that the pressure is less important in very high dimension.
Uh-huh.
Morally, can be close to the morally can be somewhat.
Okay.
Like what does break down? If anything breaks down.
Yeah, I've never thought, honestly. I mean, there are several constants that are dimension dependent, in all this story, like these 3 halves, etc. I don't know, like, where you can go. I think you can go, I mean, you can increase a bit the dimension, but not too much. Yeah, then, I mean, then also, like, for instance, then you break also the partial regularity. You cannot assume they are smooth. Yeah. I don't know. Yes. But I do believe that, like, until probably d equal 5, probably d equal 5 is the critical one, if I had to guess, for this computation due to, yeah, because stationary Navier-Stokes starts to have problem after. Yes. Okay. Now, are there other questions? Because now I switch a bit topic, and I go to non-uniqueness. Okay, if not, I would like to present you now Jia-Sverak program for non-uniqueness. And the parts I will present in detail also have a lot to do with what we will do later. And so what's the idea of Jia-Sverak? So what's the setup? We want to fix let's see how I will call it later. Yes, an initial datum which is -1 homogeneous. So it's of the form 1 over x, alpha of x over modulus of x. Okay. We want to add so this is an initial datum -1 homogeneous. And the program is, okay, first of all, I add a small parameter sigma, which at first will be very small. So for now, we look very small sigmas. First question is there a solution, a smooth self-similar solution, starting from this initial datum? The answer for sigma small is yes, and yeah, it's smooth, it's unique, because I mean, by the typical moral that when you take something very small in a critical space, the nonlinearity doesn't have the strength to beat it. Okay. So this maybe is the first theorem I will state. Okay, but maybe let me present at least orally what will be next. Then the plan is, okay, let's push sigma to be bigger. What happens to this solution? The Jia-Sverak theorem says, okay, also for sigma large, you have a solution, perhaps non-unique, from this initial datum. So every -1 homogeneous initial datum has a self-similar solution stemming from it. And this, I will say later, this is a non-trivial result because it's a large data thing. But the trick there is to realize it as something which is more explicit, like solution of the heat equation, plus something in an energy space. So this we will see later. And then the next plan will be, okay, when I increase sigma, I hope to see what is called a bifurcation. So when I change sigma, I have a curve of solutions of Navier-Stokes, each one for each sigma. Well, at a certain point, they will become true. Okay.
Sigma small, it's a self-similar solution?
Yeah, it's unique, so it's self-similar,
Okay.
basically,
Okay, so
if you want.
a bit more time.
It's, yeah, it's global. I mean, all of this is global because all of these will be in the class of self-similar, yes. Also, this happens in the self-similar class. Okay, so let me start from small data to make things more written down at least. So let U0 minus 1 homogeneous. And then the force f of xt be to be a self-similar force again, which is probably like that. And then, for every sigma small, there exists a unique self-similar solution of Navier-Stokes from sigma u0 and with force sigma f. Jia-Sverak write everything with the force 0, but for reasons that I will be clear later, let me do it in this way. Okay, and more of Navier-Stokes. Moreover, the solution u you get, u sigma, is self-similar. And the profile is smooth. As I was saying, smoothness of the profile is, it's an easy consequence, let's say, or follows from standard things. And also, when you compute derivatives of the profile in any norm you want, so let's be like ck. So the u0 in ck is bounded by a constant that depends on k, perhaps, times sigma. Okay, so the solution remains small in this sense. Okay. I'll try to give at least a nice sketch of a proof of this fact. Right, yes. So how to prove this kind of result? The first ingredient is Duhamel formula. So I want to rewrite, okay, Navier-Stokes in self-similar variables, which probably I should. Let me rewrite it. So Navier-Stokes in self-similar variables is the same as there, but with a different sign, minus u over 2, so 1/2 plus xi dot grad u. So this is Navier-Stokes in self-similar variables. And yes? Sorry?
Zero is not smooth. The initial data is not smooth.
The initial data in original variables is as a 1 over x. Is in L3 infinity. We will see. And here, as I said, we can have a force. Okay. So we write Duhamel. In fact, I write it in the original variables. So I want on the blackboard both equations plus gradient of p minus Laplacian of u minus equal to f. I apply Duhamel using as an operator the heat, and I get, so I consider the rest all as a force for Duhamel, and I get that u of tx is equal to, okay, I have to take the initial datum and let the heat act, T Laplacian. Then I have to take the force and let T act, but along the way, no? So I have to take f of s, and then I have to apply e to the time t minus s Laplacian. from 0 to t. And then I have to take this part of the equation from 0 to t, e to the t minus s, and I treat it as this one, t minus s Laplacian, divergence of u of s, u of s. Minus, where do you want a minus? On this, right. Okay, and perhaps you want also a pressure in it. Yes, in reality, the pressure you could put a Leray projector if you wanted. Okay. And now I look at the structure of this equation. So this one is the initial datum. This one is a forcing term that I call G. And this one is a bilinear operator with respect to U. Okay? So I want now to find a fixed point of this equation. And I look at an adapted fixed point. Which says that if you have a Banach space, then you fix a parameter m, a number, a point in the space X such that A is below m. A will play the role of whatever is fixed in this equation. And then you have B bilinear. Bilinear with small norm. So this is our situation. Now we have a bilinear term, but we know the norm of B from x cross x to x to be small. And here there is a quantity, the minimum of 1 over 4m and 1 over 32m squared. Then the equation u equal a plus b of uu has a unique fixed point. Okay? So to sit in this framework, we have first to decide who is the Banach space X of a function, and then show that the bilinear term is harmless. And then also get a bound on this. Okay? The norm that we will choose is the following, is the supremum of t to the 1 over 8, norm of the solution at time t in L4. This is the Banach space. And yes, and in reality, I mean, this number 4 is anything above 3. And the power of t should be adapted accordingly. And 3 is 3 because 3 is the scaling invariant one. The ingredient, so now then we will have to do estimates on this object and this object. The ingredient that so when we do estimates of this, we have the evolution of the heat equation. The heat equation, let's say, helps us. Helps in getting estimate and regularizing. No, because what do you know for when I apply the heat equation, and also in principle I differentiate, I put k derivatives in LQ. This is a constant that depends on the parameters, but I mean this estimated by the LP, the initial data, times a factor of time that depends on how many derivatives I put. One derivative pays a 1/2 for the heat equation, and how much I want to gain on the exponent q. And this gain is quantified as that, 3/2 1 over q minus 1 over q. Okay. So now, with this, having defined the norm and with these ingredients, let's look, for instance, what do we want to do first? Okay, but let's start. The first term in, so this one. The norm of e to the t Laplacian of u0 in L4 is bounded by what? By c. And then I have, t to the 3/2, and then I have a 1/4 minus 1/3 times u0 in L3. Unfortunately, u0 is -1 homogeneous, so it's not L3, but it's L3 infinity, and this estimate continues to work with LP infinity. So I have to go in a Lorentz space just because the datum is homogeneous. And what about G? Okay, so this one in particular tells me that if I estimate this quantity in the space X, I have a nice bound, no? So this implies that e to the t Laplacian u0 in X, I have to divide by t to the 1/8, which is exactly this number. This is bounded by c sigma, so it's small for sigma small. Then I have G.
Oh. Fixed, no?
Sorry?
This estimate is for t small and fixed, no? For all t?
For all t, yes. All t.
So there's a negative power of t.
There's, yeah, but I'm putting it in a norm.
Ah, okay.
Okay, then G at time t in L4. How do I do the force? This is bounded by the integral. Then I have to take e to the t minus s Laplacian of f in L4. I go down and I want to apply this inequality from 4 to 2 for a reason that will become clear. So I get the integral. So now I have t minus s to a power, which will come here. And it's minus 3/2 times 1/2 minus 1/4. So minus 3/8. And then I have the norm of f in L2. And the norm of f in L2 is the norm of, by change of variable, is the norm of capital F times a factor in S, minus 3/4. And when I integrate t minus s to the power minus 3/8 and s to the minus 3/4, I get exactly a 1 over t to the 1/8. And the norm of f in L2 gives me a sigma. So up to constants, I end up here. And again, this means that G in the space X is is controlled. What about B? I want to say another thing, so I'll try to do it first. B in L4, I use the same kind of arguments, except that now I have the integral of e to the t minus s Laplacian. Then I have a divergence of U tensor U. Ignore the pressure, or do it in the same way afterwards. And the point is, here I have a divergence. I want to use this relation by taking kappa equal 1. So I have 0t, t minus s, to a negative power, which is minus 1/2. And then I want to go from 4 to 2 in such a way that then I recover U in L4. No? I mean, here I would like U cross U in L4, in L2, sorry, because this is norm of U in L2, in L4 squared. And U in L4 is controlled by the norm of U in X. So it's S to the minus 1/4 times U in X squared. So, and this is what you want to have when you want a bilinear estimate of something. And so here the only thing is I'm missing an exponent that comes from the power gain from 4 to 2, which is a 3/8. Okay. And the point is, again, when you integrate t minus s to this power s to the minus 1/4, guess what? You get a t to the minus 1/8 norm of U in X, sorry, squared. And this is what I want on the bilinear estimate to apply. So then this fixed point gives me the result. Still have 5 minutes, good. Because then, at this point I'll only state what Jia-Sverak prove, and this is, I mean, is not far from ideas that we have introduced, energy estimates and this kind of arguments, but requires some work. So the truth is, in that theorem, I can take any sigma also big. Okay, so I have, or at least get existence for sigma big. So for every sigma in R, there exists U self-similar solution starting from U0. U0 sigma, the one that I introduced there. So U0 from any minus 1 homogeneous initial data. And you can do it also with a force, but I'll not state it because even Jia-Sverak don't do. And the key point is to try to represent the solution as the evolution, the heat evolution of your initial datum, which has infinite energy. So something which instead lies at the energy level. So L infinity L2 intersected L2H1, which is exactly the energy space. Okay. And now, what's the picture of non-uniqueness that Jia and Sverak imagine? Yes.
Something doesn't work for f equals 0.
Something?
Does not work for f equals 0.
Why?
Is that correct?
No.
Because you don't have the backwards self-similar.
No. All the point is that we are using estimates on the Laplacian, which for the backward with the minus Laplacian, and yeah. Okay. What's the picture of non-uniqueness that Jia and Sverak imagine? Let me ask.
The last blackboard with the
Yes.
square.
I'll try. Okay. Jia and Sverak imagine, want to follow and see a bifurcation of self-similar solution. So what they want to do is the following. They want to consider the curve. So look at the curve that associates to each sigma the unique for sigma small u sigma. It's not difficult to prove that when sigma is small, this curve is a smooth curve, okay? In sigma also. And now go in the realm of sigma large and try to see that this curve opens up. And the way in which it should open up, it's a dynamical systems picture, no? So they expect something like this curve of solution. So in their context, maybe this is a curve in the space of solutions. And what they expect to see is something like this, which is called a pinch-fork bifurcation. At a certain point, suddenly, I have three solutions. A model for this kind of bifurcations is an ODE. It's the ODE x dot equal with a parameter rx minus x cube. Okay. You can look at this. I'm sorry. And what do you see? So this, you look at an ODE in R. Let's say that I'm picturing here R and X. Now, x dot equals 0, so x equals 0 is the only solution for R negative. And x equal plus or minus square root of R is a solution for R positive, and also 0. Okay. And there is some extra observation that we can do. So if you look at the vector field, in these regions, all the vector field is always pointing towards 0. So all solutions that start away come to 0. In this region, they go like that. So tack and tack. And at 0, there is a peculiarity if you look at this ODE. The gradient vanishes. Okay, at R equals 0, what I mean is the first order term disappears. Okay. And there is a theorem for this kind of situations, which is called Kranдар-Rabinowitz. And we want to see somehow this kind of finite dimensional picture inside an infinite dimensional world, which is the world of solutions of. Yes.
Why do you think of such a, because you think of R being the absolute value of sigma, and you have one for positive and one for negative? Couldn't there be a different type of bifurcation with only one?
In principle, there could, but this one is expected. And yes, R is like the absolute value of sigma, but I mean, in our case, it will not be R equals 0. I mean, not sigma equals 0 is fine. We expect a certain sigma for which the linear part of the operator degenerates in some way, and suddenly you see three solutions. And the three solutions are two are, say, attractors of the dynamical system, and one is not. Everything escapes from it. Okay. Jia-Sverak. Jia-Sverak and then Guillod. The following result. Yes.
No, large sigma, your self-similar solution is not smooth, or
It's always, I think, there is no problem.
it's smooth?
It's smooth, yes. Because this is a matter of H1 being subcritical, yes. So Jia-Sverak Guillod, I'm sorry I'm late. I'll really finish this topic. What? Ah, okay. Then I was running. Okay, I was stressing out for nothing. Then I'll do much more. Fine. Jia-Sverak Guillod. So then let me see if I have something else to say about this picture. Okay, Jia-Sverak Guillod prove the following theorem. I'll state it informally still because the real statement is more complicated. So first of all, they have a result like when the linear part of the ODE vanishes, which for Jia-Sverak is the linear part is really the linearized Navier-Stokes operator around a certain profile vanishes. So let me write. If a spectral condition is verified, and this spectral condition morally is, as here, the linear part vanishing, which means and then I will enter more in detail than in the next half an hour into this, but it involves the linearized Navier-Stokes operator, and vanishing means is degenerate, so as an eigenvalue which is 0, okay? So it's not invertible, okay? Then bifurcation happens. And the spectral condition is really an eigenvalue. So maybe I should go back one step. For sigma small, if you consider the linearized operator, I'm a bit hand-waving, but I want to give some information now. Then I will enter more in detail some aspects later. But for sigma small, if you linearize Navier-Stokes around this solution, the operator is stable, okay? This can be proved. Then what they see numerically is that when you increase sigma, this linearized operator at a certain point, there is one eigenvalue which crosses the imaginary axis. So it becomes unstable. And the spectral condition that you see here is really that you want to see this eigenvalue crossing, the operator from being stable to becoming unstable. And you want to see it nice, let's say, one eigenvalue doing this crossing, not, or maybe two conjugate ones, but not 100, conditions like that. So there are some technical conditions that I don't enter too much because I want to redo this part in a different way. So then a bifurcation happens. So in the realm of self-similar solutions, then you would have non-uniqueness. And then the next step that they do is that, so there is a way one can truncate the initial datum. Because what's still the problem of a self-similar bifurcation, so similar non-uniqueness, it's not in the Leray class. But what is the philosophy now behind it? Well, the non-uniqueness is generated because in 0 you have an initial datum which is like 1 over x, whereas this initial datum is not Leray, not because of 0, but because at plus infinity you behave like 1 over x, and this is not integrable. It's not L2. So one can truncate the initial datum to get U0, which is now compactly supported. And instead, without modifying the behavior of the similar solution in 0, so in 0, you expect it goes like 1 over x, like this is similar solutions, like minus 1 homogeneous. So that there are two Leray solutions from U0. Okay. In all this story, what's missing is to verify the spectral condition, to really show that this eigenvalue crossing happens. And you see it's a delicate problem because the spectral condition is a condition on the linearized Navier-Stokes equation, but you are linearizing around something which is not explicit. It comes as a solution, as a self-similar solution of Navier-Stokes. And this, verifying the spectral condition, this was verified numerically. Okay. And this is where the numerics enters. Verified numerically doesn't mean a computer-assisted proof, but really numerics. Okay. So this is the picture of Jia-Sverak. This theorem I'm not proving is, I mean, there is some work to do. I will instead, the second part of the statement inspired a lot what I will present next and what we do in our context, and so I'll present it in another form. I'm sorry?
Two or at least two solutions?
At least two, I guess. No, I'd say at least two. But okay. So now I spoke quite a bit of this spectral condition, which involves a linearized Navier-Stokes operator. Okay, now I really want to introduce these things from the beginning. So even though maybe the last part was a bit end-wavy and maybe you were lost, now you can catch up, and maybe it will become more clear once I introduce in detail all these. Let's see if I have notes. Okay. So, and I'll do some heuristic, so the strategy, another strategy to get non-uniqueness of Leray solutions, and the heuristic will say that I'll codify it like that: self-similar instability implies non-uniqueness. Also, in this context, I'm thinking that a force is there. Yes?
When you're talking about stability, it's in the time t or in the transform time tau or not?
So the stability, maybe it will be clear in now the stability is an operator which is in space only. There is not time. But, well, let's say log time is, I think, the answer to your question, even though it will become clearer now. OK. So I fix. So I want to see how a certain instability in self-similar variables generates non-uniqueness. To do that, I fix U bar, what I consider a self-similar profile. No? Profile. And now I put back the force. So the force is a degree of freedom that enters in this precise moment, because any self-similar profile solves Navier-Stokes with the force that it's whatever expression I get for the operator computed on U bar. So it solves Navier-Stokes with force, well, whatever it has to be, no? F bar, which I'm not sure if I wrote, that's the other, but it will be minus Laplacian U bar. Then I have minus 1/2 1 plus xi dot grad U bar minus plus U bar dot grad U bar plus the gradient of P that keeps it divergence free, or Leray projecting it. And whatever the expression is here, this is in critical spaces, no? Because it's all in the self-similar realm. So in particular will be, yeah, in all self-similar spaces for the force. Now, I want to find another solution. So I look for another solution starting, OK, let me add another thing. Let's say that this profile, now that I have a force possible, I can take it C-infinity compactly supported. OK? If I take a compactly supported function, as I was saying, what is the initial datum of a self-similar profile? Is the behavior at plus infinity of my profile. If it's compactly supported, the behavior at plus infinity is just 0. So the self-similar solution generated from this profile starts from 0. I want another solution that starts at 0. And, OK, I make an ansatz, which is, in principle, very restrictive, but and different from all the ansatz that we have seen floating around today. So I make the answer that this other solution behaves like the self-similar profile, so 1 over square root of t U bar of xi, plus a small perturbation of this. So a 1 over square root of t and a small perturbation that I write in self-similar variables, xi tau. So I'm not making the ansatz that the second solution is self-similar, as Jia-Sverak do. OK? I'm making a restrictive ansatz because this U, I want always to think it as a perturbation of the other one. So it's like, I'm like saying, OK, I have this smooth profile, U bar, and I want, I don't know, the other solution to be a small, like C2 or even more, perturbation of this one. I mean, it's not clear that this should work.
X over square root of t.
Exactly, x over square root of t. But still, let's do this ansatz. And now let's try to see for this to be a solution what I have to require on this one. OK. How should I do that? So let's see. Let me think 1 second. Yes, maybe I'll write everything. For U to solve Navier-Stokes, I need U bar plus U to solve Navier-Stokes in self-similar variables. Let me write it. D tau. Then I have U bar plus U. So U bar plus U solves Navier-Stokes in forward self-similar variables, which I rewrite here, dt U bar plus U. Then I have a term which is minus 1/2 1 plus psi dot grad U bar plus U. Then I have a nonlinear term, U bar plus U dot grad U bar plus U. Then I have possibly a pressure. I don't know, P bar plus P. And then I'm missing a Laplacian, U bar plus U. And then I'm missing a force, F bar. No? This has to be solved. And then I remind myself that U bar is a self-similar profile, so it doesn't depend on time, it only depends on space. So this is not there. And then also, U bar solves this equation, okay? So I can cancel out some terms. 1/2 1 plus psi dot grad U bar is in this equation. From the nonlinear term, I want to subtract U bar plus dot grad U bar, which is one of the 4 terms appearing here. There is a pressure, and there is a Laplacian, and there is a force. Okay. So here I wrote the equation for U bar plus U, and if you want, I subtracted the equation for U bar. I get my equation. So this is if and only if. The equation that I rewrite from here is d tau U plus, minus 1/2 1 plus psi dot grad U. Then I have, what do I want to write? Maybe I write the Laplacian of U. Then I write of these 4 terms, I have 3 left. So let me write, so I have U dot grad U bar plus U bar dot grad U plus I have U dot grad U, the nonlinearity, and then I have an extra lap grad P equal to 0. This is the equation that has to be satisfied. And in what we are interested, well, if I have a solution such that as I go, so this is a solution, U of psi tau that goes to 0 as tau goes to minus infinity, okay? In self-similar variables, I recall you that time 0 in physical variables is minus infinity in self-similar. If this solution goes to 0, then this is non-uniqueness, because this formula will agree with the initial datum 0, but be different from U bar, because I'm building a U that is non-trivial. Okay, with this consideration, I'm led to consider, I want to consider solutions that are very small for very negative times. And I want to consider, I want to build it, I want to build them only for very negative times a priori. I will extend them as Leray solutions afterwards if I care. Okay. With this consideration, now we stare at the equations. And we encounter two parts in this equation. A nonlinear part, which is quadratic in U. This is the nonlinearity. And we encounter instead our nice linear part. This part of the operator is, by definition, the linearized operator in self-similar variables. Okay, if you want, with the reference vector field U bar, and evaluated as a linear operator at U. So linear in U, and depending on U bar. So this okay, and then, okay. Then the next consideration is that since I'm looking for a solution U very small for very negative times, there I expect this term, which is quadratic in U, not to count, or to count less than everything else that is in the equation. So heuristically, or let's say, I'm free to consider. So I look for solutions of the linearized problems. So theta U minus LSS U equal to 0. So ignoring the nonlinear term. And this I called lin NS. And then, at this point is where, here we start to have a linear operator, and it's where spectral analysis enters the game, because how do I find the solutions of this guy that start from -infinity and grow? This is what I want to find. Well, if I find an unstable eigenvalue, I have them. So if LSS has an unstable eigenvalue, which means a lambda such that unstable means a real part greater than 0, such that LSS of eta is the eigenfunction, is equal to lambda eta, then a simple computation tells me how to solve the semigroup. Then a solution of Navier-Stokes linearized is what I will call U-lin, which is e to the lambda tau eta. As with matrices, no? If you have an unstable eigenvalue of a 2 by 2 matrix, you can follow it to solve this equation. And then if you want to be real, maybe it's better to take the real part somewhere. Okay. And then so these heuristics to get non-uniqueness breaks down in two parts. First, I have to find a solution of this, so an unstable eigenvalue for this operator. And for that, I have the freedom to choose the profile U bar. Because as I was saying, for instance, if U bar is small, you will not find it. But we want to take U bar big in order to find that. And then the second part will be to put back the nonlinearity, okay? And for that, we will want to make an ansatz so then we make an ansatz that a solution U of, which is of the form, the linearized one plus a perturbation. With the perturbation in some norm that for now I don't specify. Twice as small as the U-lin. Now the U-lin grows as e to the real part of lambda tau. Okay, here, if I want it twice as small, because the equation is quadratic, I will have a 2. So now I want to make the ansatz that this solves the original problem. The original problem has U, then LSSU equal U dot grad or plus. Sorry?
The exponential is 1/2 because it start to be smaller than the other.
Smaller is higher power because, I mean, tau is very negative.
Tau is negative.
So, yeah,
Okay.
higher power means smaller. Okay, so this ends the heuristic. And at the end of the heuristic, we know what we want to prove. And this we will prove tomorrow, I guess. What time is it? 1 minute, perfect. So let me just state this. So an effective theorem that gives non-uniqueness, but with much more information than just there are two Leray solutions, is, so there exists U bar, which is a profile, C infinity C, and divergence free, because of course I want to solve such that first part of the theorem is a linear statement, linear instability. LSS has an unstable eigenvalue. Second part of the statement. So as an stable eigenvalue eta with eigenfunctions lambda. And as I did before, call U-lin, whatever I called there, no? The solution of the linearized problem that stems from it. Second part, there exists T, and so now I want to really solve the nonlinear problem. I want to look for a function that I call U perturbation, which, such that, as I was saying, U pair has to be small, and now I quantify it in HK up to a K dependent constant, e to the 2 re lambda tau, for every tau less than T. T is a priori very negative. I mean, it's a parameter that I can take very negative. So such that the associated U bar of xt, which is 1 over square root of t, capital U bar of x over square root of t. And the one associated to, so u of xt, which is associated to 1 over square root of t, and then I have u bar plus u lin plus u pair at x over square root of t tau. These are two solutions, two distinct solutions of Navier-Stokes from initial datum 0. And with force, which has the expression, and with a force that is the one here. OK. So I stop here. Tomorrow we prove the two parts in this statement.